This is the 10th episode, and as you can see in the title, I'm counting the episodes in hexadecimal. I'm wondering if the Google algorithm will screw this up with the next suggested video. Anyway, I want to explain in this video why hexadecimal is cool and why you should use it when it comes to computers. I will also show you how I convert values back and forth and how I often work with them. Okay, so all computers work in binary, zeros and ones. Because it is a representation of the physical behavior of our circuits that we have transistors that are like switches and they are either turned on or off. A single value that is either 0 or 1 is called a bit. You may know that a byte is 8 bits, but maybe you wonder why that is. Well, this was not always the case. Early computers might have had 6 bits per byte. That we use 8 bits for a byte nowadays is just how history turned out. It was IBM's fault with the System 360 that heavily pushed for an 8-bit byte. Also, some people say the octet instead of byte to make clear that they mean 8-bit. An interesting example is ASCII, because you will notice that it actually only uses 7-bit, but because we now generally use 8-bit bytes, we kinda waste the first bit. We humans grew up with the decimal system. We are used to counting with symbols from 0 to 9. But that is rather arbitrary. Sure, we have 10 fingers, but we could also count in 12s, because we have 12 finger bones and we can use the thumb to point to which number we are at. This is the duodecimal system, and we actually use it on our clock. So if you would have grown up with counting in hexabinary, it would feel as natural to you. Instead of thinking of numbers as something fixed, think of it as a tool, and you can use whichever number system makes sense for a particular problem. So our computers work with bits, and for our modern computers we have defined that we generally work with bytes of 8 bits. And 16-bit, 32-bit or 64-bit architectures are just playing with the value to keep it nicely divisible by 8. When we look at the data as raw bits, 0000000, we quickly see that a byte takes a lot of space if we display it in that way. Maybe decimal would be a cool representation. It certainly would take less space to display them. I will use Python now to show you how we can convert binary to decimal numbers. We simply say that the string represents a number in base 2. Let's do it for a couple of examples with a simple for loop. Okay, well, takes less space, though it kinda bothers me that the biggest value with 8-bit is a weird number in decimal, a number without any interesting properties or meanings. Let's have a look at those numbers in hex. Hex numbers are symbols from 0 to 9 and A to F to describe a number. We can extend our loop in Python. Now you can see how pretty hexadecimal numbers are to represent 8 bits. The biggest 8-bit value is also the biggest value in hex that can be represented by 2 digits. If we would add one more bit, so we have 9 bits, we would also have to add another digit. And not only that, if you look closely, it also nicely represents the 2 individual nibbles, that means the 4 bits. So an 8-bit number in hex can be represented by 2 symbols, and each symbol refers to one nibble. So this makes it very, very clear and easy to read. And now you can understand why the decimal representation is not very fitting for this kind of stuff. For example, can you tell me what is the maximum number that an unsigned 32-bit integer can represent? Well, I don't know in decimal. I just know that 32-bit is 4 times 8-bit, and thus maxint is FFFF. Now, let me quickly show you some cool tricks with Python to convert stuff back and forth. Python has some built-in functions to convert numbers, so for example hex and bin, and also to parse a binary or hex number with the int function and specifying which base it is. If you have a binary string, this means that maybe not every value in the string is a nice ASCII printable character. You can use encode and decode on the string to get the hex representation of the characters. So hex for 1 is capital A in ASCII. A much more powerful and important functionality is offered by Python structs, which I use all the time when I deal with binary data. First import struct, and then we can use struct unpacked on our data. In this case, I define that the data is an unsigned integer. And you can see I can convert this binary data now to an integer number. If you look closely, you may wonder why the capital A seems to be at the end of the number. The reason for that is that we have a little endian system. Bits can be interpreted in two ways. Either the first or the last bit can refer to the least significant bit. I think the picture on Wikipedia makes this very clear. This can be very important when you receive data from a big endian system, because then you have to be careful how you interpret this data. But with Python structs it's easy, and we can define as which endian system we want to interpret this data. If you watch some of my CTF exploitation challenge videos, you will see me using Python structs a lot, because it's great to convert addresses and other data back and forth. For example, if we want to override an address, we have to supply the data as a string, so we can use struct pack and pack a number as a binary string. So the hexadecimal system makes working with computers much more simple, and you should get used to it. But we just talked about positive numbers, from 0 to FF. But how can we represent negative numbers? Maybe you have heard of the signed bit, that the first bit tells you if this is a negative number or not. Though it's not as simple as reading the remaining 7 bit and deciding if it's positive or negative based on the first one. -1 is actually FF. Well, it does have the first bit set, but it's not -127. This will maybe makes it a bit more clear how the negative numbers are actually interpreted. To convert a number to its negative value, you simply invert the bits and add 1. It's called the 2's complement, and this system has the advantage that fundamental arithmetic operations like addition, subtraction, and multiplication are identical to those for unsigned binary numbers. You should read the Wikipedia article about it, that should make it clear. Many functions return -1 on error. At first it sounds weird, but now you know that this is just all f's, and when you read data and you get only 1's or f's in hex, you might read an error. What about numbers with fractions? Well, don't get me started on that, it gets really ugly. But you can guess that representing a value with many digits behind the comma can get very creative if you have only 1's and 0's. Now before we end, let's get a summary of the terminology. We start with a bit, 0 or 1. 4 bits are a nibble. 8 bits are a byte. And in hexadecimal, we can represent a byte with 2 digits. On 32-bit architectures, a word refers to 32-bit or 4 bytes. But on 64-bit architecture, a word is 64-bit or 8 bytes. And a double word is obviously the double amount of that. As you can see, a computer only has bits, and how we deal with those bits is up to our interpretation. I know this was a bit shorter and less technical video, but I thought it fits, and next time we will dive deep and exploit our first buffer overflow.